should start by thanking the organisers. This is my first visit to Brazil, so it's exciting. But as the last speaker, it's also my privilege to ask everyone else to join me with thanking the organisers for bringing us all here today. So maybe we can start by saying thank you. Okay, so I'm going to be talking about tropical schemes. So this is, in a sense, a continuation, well, in the same theme as Jeff's, though I will be more somehow lower technology and more explicit about a few smaller examples. And this is all, except for when I say otherwise, joint work with Felipe Rinken. So the goal is to introduce a new definition of just, I want to say, a sub-scheme of tropical projective space that is not necessarily the tropicalization of a scheme. But before I do that, I want to work my way up by sort of repeating what Jeff said in the case of subschemes of projective space. So the notation will be, for me, I'm a min person, so I'll have the tropical semi-ring with operations tropical addition and time. So this is R union infinity, and this is min. Okay, and so we're going to start, if we want to tropicalize, we fix a field K with a valuation, and being a min person, my valuations go the opposite direction from Jeff's. So the standard one, so val from K to R bar, that's R union infinity. And then we want, for a polynomial F, which I might write as F being the sum of Cu x to the u in the polynomial ring in my n+1 variables, then I'm just going to say trop F, as we all know, is the valuation of the tropical sum of the valuation of Cu times x to the u, so that's just the minimum of the valuation of Cu plus x dot u. Okay, so we're just going over, we haven't had as much embedded tropicalization this week, so I just want to quickly review this so we say what we're generalizing. So our tropical hypersurface, in my notation, is just the set of W in R to the N or R bar to the N. Well, actually, I want to say, I guess here I'll talk about tropical projective space. Yes, such that the minimum in trop F is achieved at least twice. And so trop Pn is just R bar to the n+1, take away infinity to the n, mod R. Okay. So as we all know, if we start with y in projective space, then trop y is just the intersection for f. Maybe y is the projective variety defined by an ideal I. So we take f in I of trop v of f, or equivalently, it's the closure of the valuation applied to y. Okay, so the main fact we know about tropicalizations is the theorem that we normally attribute to Berry and Groves et al., which is the structure theorem saying that these are polyhedral complexes. So we can say here that trop, so here I'll assume y is irreducible. So trop y is the support of a weighted balanced so inval rational polyhedral complex. So this is the theorem I want to compare against. So let me make sure it's clear what I mean by this. So by inval rational, we have a polyhedral complex. All the facet directions are rational, but the vertices can be in, well, the vertices, let's say, up to waving my hands, the vertices can be in the image of the valuation. So I might have real entries for the vertices of my polyhedra, but my facet directions are rational. And the weighted, we remember this means we have an intrinsic weight, well, integer weight on each maximal cell. And by intrinsic, I mean determined by y. So each maximal cell of the polyhedral complex such that this satisfies the balancing condition. Okay. And so the weights turn trop y is a tropical cycle, which we heard about in Kristen's talk. Is a tropical cycle. Okay, so that's the tropical variety sort of background in the way I want to talk about it. And as we all know, we're all here because we believe that this is a useful theory. This and its other versions are a useful theory, that we can get things out of it. We heard in Ilya's talks about the enumerative successors and so on. But there are also some issues which are also well known. I mean, the most elementary issue is, I guess the problem is that we don't have all of elementary algebraic geometry. So one elementary issue is the lack of irreducible decomposition. And I should have started this on the So let me draw the picture over here. This is the fact, the most basic example is if I take 3 lines, I can write this. So this could be written as this union, this union, this, or it's also the standard tropical line union a tropical conic. Okay, so when we see this picture, we don't know what the irreducible decomposition is. So that's an issue from having a standard sort of theory of elementary algebraic geometry. And the other main issue that is, or complication, is the fact, which is also well known and studied by many people in this room, is the fact is sort of realizability issues. So let me say relative realizability issues. So this is the fact that not every object that looks like a tropical variety is actually the tropicalization of this. And maybe one of the more glaring examples, which has been well studied and partially at least understood by some people in this room, noticeably Eric and Kristen, it would be Vigeland's examples that there exists a smooth tropical cubic surface with infinitely many lines. Cubic surface with infinitely many lines. So of course, classically, we expect on a cubic surface we should have 27 lines. So infinitely many lines is a problem. Okay. So what can we do about this? Well, one answer for anything is to try and go, add more technology. So the question here is, what can we do about tropical schemes? So let's remind ourselves that classically, I'm going to just restrict myself for the talk to subschemes of projective space. As Jeff's already told you, this works more generally for subschemes of toric varieties, or more generally F1 and objects over F1. So let's start here with a subscheme of projective space. So a subscheme Z of Pn is given by a homogeneous ideal I contained in K adjoin x naught up to xn. And then we just say that Z is proj of K adjoin x naught up to xn mod I. Okay, so This gives us a way of getting a geometric space from our ideal. And you could also think, yeah. Okay, so this is what we want to tropicalize. So we now go through and we just tropicalize each ingredient. The polynomial ring is straightforward, but let's still spend a few moments on it. So we can start to tropicalize that. We'll get R bar adjoint x naught up to xn is the semi-ring of tropical polynomials. Okay, so all operations here should be tropical operations, right? So the multiplication, you've got coefficients in the tropical semi-ring. Multiplication is tropical multiplication, so addition. Addition is tropical addition, so minimum. I just wanted to make a note here that I really want polynomials, not functions. So what do I mean by this? I mean x squared plus 7xy plus y squared is not equal to x squared plus y squared. Okay, so I want to regard these as different polynomials, even though the minimum, so even though the minimum of 2x, x plus y plus 7, and 2y equals the minimum of 2x and 2y for all x and y. Okay, and the reason for this is that this will make it more straightforward to define what sort of ideals I want to talk about later. Okay. So given if I start with a homogeneous ideal I in the semi-ring of tropical polynomials, so I can tropicalize it. We saw that in Jeff's talk. So given a homogeneous ideal I contained in K adjoint x naught up to xn, we'll take trop of I is just going to be the ideal generated by trop of f for f in I. Okay, so my angle brackets means ideal generated by, and I find for everything in semi-rings, you always have to pause and check, all these elementary algebra operations, you have to pause and check, yes, they still are true in semi-rings the way they think. So this does work the way that you think it does. However, this is almost never finitely generated. So let me say almost never finitely generated.
Which ideal do you mean submodel?
By ideal, I mean, so yeah, R submodel. So something, it's closed under addition and multiplication by things in the semi-ring of.
Maybe it's useful to point out that when you say the ideal generated by trop f, actually it's enough to just take the thing which is spanned by all those trop f's. And that will already be an ideal.
Sure, yeah. Yes. So what I want to emphasize, though, is that even if you start with a very simple ideal, this ideal can be a complicated thing algebraically. So here's the most elementary example. If I start with I being x squared plus xy plus y squared, this is a classical ideal before I tropicalize. It doesn't matter what the field is, but it's a principal ideal. So let's call this polynomial f. So then trop f is x squared plus xy plus y squared. Okay. Now the one thing we have to remember about the tropical semi-ring is we don't have subtraction. So everything in the ideal generated by this polynomial is going to have at least 3 terms. Okay? No matter what you multiply, you multiply this polynomial by any other polynomial, there will be at least 3 different monomials that show up. However, we have x cubed minus y cubed is in I. Okay, just multiply this by x minus y. So x cubed tropical plus y cubed is in trop I. but it's not in the ideal generated by trop F. Okay, because it has only two monomials showing up. Okay, and now you can generalize this. You can check. I mean, by the same argument, you're going to get. You can replace the 3's by your favorite power of n, and so you're going to find out that this ideal is not, is not finally generated in this way. Okay, so that's just a sort of a warning that these things quickly become nastier than you'd expect. Okay, so the definition which we saw in a variant last time, so we are trying to tropicalize this. We know what's going on there. We know what's going on there. So we'd like to say, so for Z being proj of k join x naught up to xn mod I, we're going to define the tropicalization of Z to be, well, we start with R bar adjoin x naught up to xn. Naively, you quotient by trop I. However, in a semi-ring, we don't want to quotient by ideals. This is where you go back and you remember, why do we introduce ideals in your algebra class in the first place? It's because ideals are kernels of homomorphisms. In a semi-ring, because we don't have subtraction, we have to remember not just what gets set to 0, but what gets identified under the homomorphism. So the pre-images of any point in the image. So I'm going to write just congruence of this. This is the, maybe I should call this the script. This is the script B from Jeff's talk. So for every polynomial in the trop I, you do the bed relations we saw in the previous talk, and that gives you a congruence, so a way of identifying things, and we can quotient. That gives us something we can actually quotient by. Okay, and then we say proj here. And again, you're allowed to complain that we're taking proj of a semi-ring, but then this is something that, as Jeff explained, in some sense, the F1 thing. In fact, you could say that this is why we are in this room right now, at least half why we are in this room right now, because this is the connection with F1 geometry and what brings Oliver to the story. Okay, so this is our tropicalization. So what do we know about it? Well, I guess Jeff already said this in the previous talk. We know that from this you can recover the tropical variety. So the theorem, the first part, I'll say Gen Syracusa, is that trop y, so this is, we want to say, well, let's just say the tropicalization of Z can be recovered. So the tropicalization, let's say, so Z is proj k join x naught up to xn mod I. And then let me just write y for the variety of I, meaning just the point set. So just the, the underlying reduced variety. So trop y can be recovered from trop Z. So here I'm saying, here this algebraic, the tropicalization of the scheme. Here we're meaning just the subset of points in tropical projective space. So we can get, so this is the scheme remembers the variety. Okay, so that's a good property. Second property, we have result of mine with Felipe. The weights on trop y can be recovered from trop Z. Okay, so that this is the scheme remembers the cycle. So these are, we're saying, if you give me this object here, from it you can get the set of points, which are the tropical variety, together with the multiplicities. And if you think these two are necessary conditions for a meaningful scheme theory, right? We have to historically, we have varieties, we had cycles, even in I guess in the 19th century, and then we have the schemes from the 20th century, and these are all meant to build on one another. Okay. The question, though, that I want to spend the rest of my time on is, this is a story about tropicalizing classical objects. We would like a more intrinsic tropical definition that we could then use to sort of work with in the same way that we work with tropical varieties as subsets and try and prove theorems about in a tropical category instead of dealing only with tropicalizations. Right? This is meant to give us a bit more freedom and maybe make the theorems easier to prove. So the question is there a more, let me just say, tropical definition? Okay, so first, the tempting definition is, and let me tell it to you and then tell you why I don't like it as a definition, is we could just say let J be a homogeneous ideal in my semi-ring of tropical polynomials, so R bar adjoint x naught up to xn. And then we can say, we could say proj of R bar adjoint x naught up to xn mod J, or mod the congruence of J, or the bed relations of J. That's a natural choice. Okay, so let me now tell you why I don't want to just make that as the choice. Okay, so this looks identical to the definition that I had over here. Right? I started with an ideal, I got a tropical ideal, and then every other operation I did was just take the congruence quotient, take proj in this F1 sense. What don't I like about that? The problem comes when we try and take the underlying tropical variety, in that we don't get things that look like tropical, that we're prepared to accept as tropical varieties. So the problem is so V of J, which is just the set of W in trop Pn, such that the minimum in F of W is achieved at least twice, can be a fairly arbitrary union of convex sets. Fairly arbitrary union of convex sets. Okay. So let me tell you, give me sort of a bit more, I mean, not quite a concrete example, but a way towards seeing why this is the case. The issue is, the issue is coming down again to the fact that the semi-ring of tropical polynomials is not Noetherian, so you can have an infinite number of independent conditions. So let's start with an elementary example. If I look at the set of x in Rn such that u dot x is 0 and v dot x is greater than or equal to 0. Okay, so this is for u and v in Rn. Okay, so we're just looking at a rational half plane. A rational half hyperplane. Okay, I've got the hyperplane u dot x equals 0, and then I'm cutting that in half with v dot x greater than 0. Okay, so this set equals the variety of, well, I can look at the ideal generated by the x to the u plus x to the u minus, and then I'm going to write it as if I'm Laurent polynomials, though we could clear denominators. Okay, so I'm just going to take two polynomials. The first is just the binomial u plus, so u is u plus minus u minus, and u plus and u minus are in n to the n. Okay, so here we have a binomial. Being in the variety of this binomial just means that w dot u plus equals w dot u minus, or in other words, hence w dot u is 0. Being in the variety of this means that the minimum of w dot v, w dot u, and 0 is achieved at least twice. But we just said that w dot u was 0, so w dot u and 0 are achieved twice, so this one must be non-negative. Okay, this can't be the minimum. Okay, so we're saying this set equals this variety. Okay, so now what do? Now you've got a rational hyperplane. Well, now you can draw a picture like, imagine that this is a circle inside a plane in R3, and then maybe I've got some line coming out of the plane. Okay, I get the circle by writing it as an infinite intersection of rational or hyperplanes, so rational half spaces inside this hyperplane. And then to get the line, I could get the line similarly, and then I just intersect to take the union. Okay, so what we're seeing is that these varieties could be pretty arbitrary. Okay, in particular, we don't want to somehow allow a circle as a tropical variety. Okay, so what's the solution? The solution is to be fussier about what sort of ideals we put in. And this is to think about what's going on in the realizable case. So the solution, okay, for homogeneous I contained in the standard polynomial ring, we know that the dth graded piece of I is a subspace of my polynomials of degree d. Okay, so when we tropicalize a subspace, we should get a tropical subspace or a tropical linear space. Okay, so trop ID is a tropical linear space well, just as this as a vector space, it would naturally go in R bar to the n plus d choose d, because this is the dimension of the polynomials of degree d. Okay, so this is what we want to generalize. We're going to just now turn this fact about realizable things into a definition. Okay, so we start by saying a tropical ideal is going to be an ideal in the semi-ring of tropical polynomials with this property that in each degree we have this tropical linear space condition. So definition, a tropical ideal is a homogeneous ideal J contained in R bar adjoint x naught up to xn, for which JD determines I'll put the word valuated in parentheses, we'll say a valuated matroid for each D greater than or equal to 1. So this evaluated matroid, and I should have said on the set of monomials x to the u such that the degree of x to the u is d. Okay, so we've got, so what do I mean this? We've heard a bunch about matroids this week already. The idea is matroids are what happens when you tropicalize a subspace. Okay, in the constant coefficients, we just remember the combinatorial data of the matroid. If we're non-constant coefficients, then we remember what's called the valuated matroid. This is keeping track more or less of the valuations of the bases of my matroid. So we're keeping some extra data. If you want to have a tropical line that looks like this, then you're really remembering valuated matroid data. And what do I mean by determined? The idea in the constant coefficient in case, the idea is that the polynomials in the ideal should be the cycles, which means unions of circuits, of the corresponding matroid. So the supports of polynomials of degree d, yeah, I guess the supports are minimal supports of polynomials of degree d should be the set of circuits of a matroid. Okay, so that's a combinatorial condition. Not every ideal satisfies it. So let's just say non-EG. E would be the ideal generated by x plus y. Okay, why is it not an ideal? Because in degree 2, we have I2 contains x squared plus xy and xy plus y squared, but it doesn't contain something like x squared plus y squared. Okay, so this is my non-example here. Okay, so the definition, and I guess the example is anything of the form trop I, where I is an ideal in K adjoin x naught up to xn. Okay, so the definition then is we want to define a tropical subscheme of tropical projective space to be proj of the polynomial semi-ring of tropical polynomials quotiented by the congruence of one of these ideals. So the definition is a tropical subscheme of tropical projective space is proj or R bar adjoint x naught up to xn quotiented by the congruence of j, E for j contained in R bar adjoint x naught up to xn, a tropical ideal. Okay. So what is this good for? Well, or rather, why is this a good definition? So the justification is the following theorem. So first of all, well, let me tell you essentially what do we know about these objects. So this is, again, with Felipe. So if J is a tropical ideal, then the variety of J is the support of a finite R-rational polyhedral complex. Okay, so what do we mean? So we saw in the pictures, which I guess I just erased, that if we don't put the tropical ideal condition down, then the variety of an ideal in the semi-ring of tropical polynomials can be fairly arbitrary. Okay. What we're saying here, it's a support of a finite polyhedral complex. What do I mean by R-rational? This means, again, the facet directions are rational, but the vertices might be real. Okay, so we're writing it in the polyhedra have the form AX less than or equal to B, where A is a rational matrix, B is a possibly real vector. Okay, so this is the first good news. We would like, of course, to actually have the theorem, which I stated near the start of the Berry-Groves theorem. We would like to be able to say, okay, if this is a prime ideal or if the variety is irreducible, whatever that means in this context, then this has the correct dimension and it's balanced. Well, at the start of the week, we were being all gung-ho optimistic that we might finally finish that by now, but we're still optimistic that that is true. So we do believe that belief is a funny thing before you have a proof, but I think we do believe that we should be able to, that the statement of this part of the theorem should look exactly like the Berry-Groves theorem. Okay, second part is there are tropical ideals not of the form trop I for I contained in K join x naught up to xn. Okay, so not everything is just, I mean, I said this was my main example, the motivating example, that tropicalization of an ideal gives you one of these tropical ideals. But not everything comes in this way. And I mean, this, this is this good news or bad news? Well, it's bad news from the point of having a nice axiomatization, but it's good news from the same reason that having an it gives us an axiomatization we can actually use. Right? So you should think this is like having matroids instead of realizable matroids. Okay? Maybe most useful is I told you that the semi-ring of tropical polynomials is very non-Noetherian. Okay? We saw that if we tropicalized a principal ideal, then we got an infinitely generated ideal. Okay? So it's very non-Noetherian. But the good news is that tropical ideals satisfy the ascending chain condition still. So tropical ideals satisfy the ACC. And what do I mean by that? So there does not exist J1 properly contained in J2, properly contained in J3, properly contained in ... with all Ji tropical ideals. If I remove the tropical adjective here, then this has to be false, because for the same reason that in the normal polynomial, in usual commutative rings, Noetherian is either ACC or finitely generated. So because it's not finitely generated, you can get a sequence of ideals going, of increasing sequence of ideals, but it won't be they won't all be tropical ideals. So there's only going to be a finite ascending chain of tropical ideals. And this is good news because this gives us some formal consequences, right? So we can define a tropical ideal to be irreducible. Yeah, question?
If you have a set of generators, can you talk about the smallest tropical ideal?
Containing yeah. So yeah, there's a problem that it's not. I mean, this comes down to the question. I mean, it comes down to a matroid question of if I give you some dependent sets for a matroid, can you fill it in? And in general, this is not unique. In fact, it's. I mean, that statement, as I phrased it, is sort of trivially not. It is never unique unless I've given you all the dependent sets of the matroid. So yeah, so it's somehow. Sort of, you can't talk about the tropical ideal generated by a finite number of things. However, I mean, this is the thing that I think we still don't understand, right? That this suggests there is some finiteness going on, right? But I think we don't yet know what that finiteness is. So the good thing about this, we do get some formal consequences, though, right? So if I say, well, let's just say corollary, irreducible decompositions exist. So that means we're going to say if I is irreducible, if there does not exist tropical ideals J and K with I equals J intersect K. Okay, so now you're at the level of varieties. This should be saying the variety of I is the union of the variety of J and the variety of K. And so what does that say? Well, so this is just a formal consequence of the ascending chain condition, right? This is a few line proof now. It's exactly the same as the standard proof in elementary algebraic geometry or commutative algebra. Okay, so let's come back to the standard counterexample, the standard example of y that I gave you at the start of my 3 lines. So in order to talk about this, I have to give you 2 different tropical ideals that have this as their variety. Okay, and I'm going to choose 2 realizable ideals. Okay, so in this we could realize this as classically as the variety of x minus y, x minus z, U and Y minus Z. Okay, this is the U. So maybe think of this as I've suppressed the Z direction. In the tropical variety, I've quotiented by 1, 1, 1. So I have this. So let's take I actually to be generated by this. Okay, and let's take I prime to be generated by x plus y plus z times xy plus xz plus yz. Okay, so tropically, classically, this is the union of my 3 lines, and they tropicalize to the 3 straight lines you can see here. This is the union of a line and a conic, and this tropicalizes to the standard line and this backwards conic. Okay, so now if I take this trick and I tropicalize the ideals, what happens? So if I take J to be trop I and J prime to be trop I prime, so the first thing you notice, let me actually do this one slowly, is if I multiply this out, what monomials show up? I get so J3 equals J prime 3, which is just generated by, it's just the R submodule generated by, we have every, might be easier if I draw the picture, we have every monomial except for the cubic. So we have x cubed, x squared y plus x y squared plus x u squared z plus x z squared plus x y z plus y squared z plus yz squared. Okay, so in degree 3, these ideals are the same, but in degree 4, they're different. Okay, in degree 4, you could say f, which is x squared minus y squared, x minus z, y minus z. This is an I, and so trop f is in, say, the degree 4 part of J, but not in the degree 4 part of J prime. Okay. And so what we're seeing is, in this case, the degree 4 part of my I'm thinking of the tropicalization of I as so J and J prime is giving me the scheme structures on these 2 sets, and we're seeing the degree 4 part of the ideal is telling us the difference between these 2. And then, okay, being a bit sloppy here, it's possible that to really make sure that the intersections work correctly tropically, you might have to put some more generic coefficients here. But in principle, once you've done that, then J and J prime should have the intersection properties that we want. So they should actually decompose as the union of either 3 or 2 tropical ideals. Okay, so that's the first bit. And maybe the last part I want to say is, so another advantage is we get some, I think we're starting to see some information about realizability. You know, as I think probably everyone who's thought about this question would agree, it's impossible, sort of for matroid, whatever reasons, to really say anything about realizability in a full sense, but what we can still hope to rule out some cases. So let me come back to the case. So the only case we've actually settled so far is the case that has already been settled for several years, and this is sort of work of Bogart-Katz and Brugele-Shaw and others. So this is Vigeland's tropical lines. So tropical schemes also rule out Vigeland's infinite family of lines on a smooth tropical surface. Okay, so as I've said, there's already at least 2 proofs in the literature that that rule this out. So what I'm going to do, in some sense, follows more closely the Bogart-Katz one. So,
One falling for that.
sorry?
One falling for that.
Yeah. So how does this work? There's a vertex. So what we have here is we have some smooth tropical surface. So you've got some polyhedral complex of dimension 2 in R3 with three two-dimensional things going in each of the standard directions. And it contains, there's an infinite family of tropical lines contained in it. So if you actually look at Vigeland's construction here, what we actually see is there is a vertex W of the tropical surface S that is a vertex of infinitely many tropical lines contained in the tropical surface. So what we're seeing here is a vertex of infinitely many tropical lines. Let's call them in L alpha contained in S. Okay. So now you say to yourself, well, suppose this was realizable. I mean, how are we going to rule out the fact that these, other than proving that there's only finitely 27 lines on a smooth cubic surface, so of course these can't all be realizable. How can we directly tropically see that all of these are not the tropicalizations of lines on a cubic surface? So the approach is to say, if S is the variety of F for some F in R bar adjoin x0 up to x1, x2, x3, in degree 3, and L alpha is the variety of I alpha for I L alpha contained in x0 up to x3, with we'd better have F in I L alpha. Okay, so these are, that should be an R bar. These are tropical ideals here, right? We're supposing, so we're supposing that this is a tropical ideal of a line. Or in other words, the tropicalization of a line, then we're going to get a contradiction. Right? And how does this go? Well, so this is the bit in which we follow Bogart-Katz, is to say, and I guess I should say, this time we is with Simon Hamper. So this is, the calculation is so in this case, what are we going to do? You say, well, if we have this, then the initial term of F with respect to my W has to be in the initial ideal with respect to W of IL alpha. Okay, so I haven't told you what these objects are precisely, but maybe it's not so shocking to know that in the same way that we have a Grosvenor theory in the standard polynomial ring, then we also have a Grosvenor theory in the semi-ring of tropical polynomials. So I can pass to a degeneration. And this is an ideal it's in the tropical semi-ring, but it's also in the smaller one with coefficients in the Boolean semi-ring, which is just 0 and infinity. Okay, so when you pass to an initial ideal, you get an ideal in this Boolean semi-ring. The good thing about this is that this initial ideal is the same for all alpha. So it does not depend on alpha. So here, alpha was meant to be my parameter in this infinite family. So we had an infinite family of lines, of ideals, which maybe all contain this polynomial f. When we pass to the initial thing, ideals, we get this initial form contained in this initial ideal, and this doesn't depend on alpha. Okay, so that's the story that would have to be the case. The good news is that we know what this is. So this is a polynomial with 4 terms, and this is also easy determined. And then what you do is you say, this is a polynomial of degree 3. If this is going to be a tropical ideal, that means I look at the matroid it determines in degree 3, and these are independent in the degree 3 matroid of the initial ideal with respect to L alpha. Okay, so what we're saying is, if this was contained in here, this would be a dependent set, and so these terms would not be independent in this matroid. So it turns into just a matroid calculation in the polynomials. I guess, sorry, this should be a 3. So in a matroid whose ground set is the monomials of degree 3 in 4 variables. Okay, so you do this calculation, and that rules out this Vigeland line. Okay, so that's sort of a first, I mean, admittedly already done, but a first application of using these sort of techniques to rule out these relative realizability questions.
Can you repeat the condition that rules it out?
Well, so the sentence said if it was relatively realizable, then, well, first of all, there would be a classical, I guess I didn't say that, there would be a classical F and a classical IL. So in particular, when you tropicalized, you'd get a tropical thing, and you would get a tropical ideal of a line containing my polynomial F. When you pass to the initial term, you get one polynomial with a specific polynomial with 4 terms. I mean, for those who've thought about tropical cubic surfaces, this is the vertices of the simplex corresponding to that vertex. Here, we also know what that line is. It turns out the key fact here is that there's no choice for the tropical scheme structure on this line, of a realizable line. So there's the realization space of the relevant matroid is just 1 point up to PGL. So we know what the scheme structure has to be here, and they're not compatible. This polynomial, there's no polynomial with this support in this ideal. So from that, we can conclude that all of this is sort of a purely a different, well, as I said, it's following, at least at the start, the Bogart-Katz approach, but another way, a tropical way to rule out the realizability of the Vigeland lines. And so, I mean, clearly, one place to go from here is to try and come back to these other relative realizability questions and questions of other lines and curves on surfaces and high-dimensional varieties. But so, I guess that these two were meant to be the sort of the first proofs of concept to say we're introducing this new theory of tropical schemes, and here's what we're hoping we will be able to say more about in the next year or so. But I think it's there's a lot more to go from here. So maybe I'll stop there. Thank you.